Good morning, I'm on site here at Embedded World 2022 and joining me today is Martin Kellermann, the Marketing Business Development Manager at Microchip. So thank you very much for joining me this morning. Now we're going to be talking about Microchip's FPGAs. So before we move on to FPGAs in more detail, when we've spoken before, you've described them as sort of Lego for engineers, predefined small building blocks out of which you can build fantastic applications. Now I found this really intriguing. So could you sort of try and define FPGAs in relation to this analogy?
Yeah, sure, Paige. So that analogy was coming up when I was playing with the Legos of my children.
Yeah.
As usual, as it happens, Dad just takes it. And what I really saw there was you have those predefined blocks in the box. They all match together and you can build really, depending on what you want to do, you can build completely different things.
Yeah.
Always on the same base blocks, but then depending on where you want to go, different plans, different ideas you have, it will become something completely different. It may be a car, it may be a house, it may be whatever.
Yeah.
And that is actually exactly the same on FPGAs. You have the predefined building blocks, you have lookup tables, you have flip-flops, you have more complex components like the DSP blocks or block RAMs, and they also match together. It's something where different ideas, different specifications instead of just plans will really create something completely different on the completely same architecture. So one family member may be a medical device, next one may be an industrial controller or even something in aerospace. So something really, the complete flexibility matching together.
Yeah, can really let your imagination run wild, it's great.
Exactly.
So would you like to walk me through some typical applications of your FPGAs?
So on our FPGA portfolio, it's typically, we have different family members and different generations of FPGAs. And those different generations are not replacements, but add-ons.
Okay.
So we have different generations of FPGAs, which are completely valid besides each other. And that also means we have different sizes, different complexities of the FPGA. And that also means we then do really very different application classes. If we concentrate on the latest generation, PolarFire SoC, that's something where we see a lot of traction in industrial market, automotive market, and also very especially on the vision market. And in there, the key elements of our FPGAs, the low power, the small footprint, they are really the ones that are kicking in and which are giving the benefit for those applications. So one application may be a medical device like a transducer for ultrasound, handheld, and then connected to a smartphone as a display for point-of-care situations. And that's something where the small footprint of those FPGAs and the small power footprint absolutely kicks in. And the small power footprint, or the small physical footprint, is something that you can also see here on those devices. Just putting here a cent coin towards the PolarFire and the small FCSG 325 package, 11 by 11. Those are devices, 50,000, 100,000 logic elements, where you can really do a lot already in a small footprint, together with a small power envelope. And some other applications, for example, cameras, smart embedded vision. If you imagine you have a camera the size of a cigarette box, you can't do a lot of material in there. You have to be small, you have to have the right performance per watt, and you also need to stay within the thermal envelope. So something that we do enable with the PolarFire devices, and where we have a strong traction in that vision market.
Brilliant.
Based on those things.
Yeah, fantastic. So what is the main difference and differentiator of Microchip FPGAs and system on chips?
So main difference, I would say, it's the focus.
Okay.
So it's really a mental thing, the focus on where we want to play. We're concentrating on the mid-range market. And that means after that decision, we could really also gear our devices towards that. Means we made architectural decisions, we made technology decisions, and all those are bringing us some differentiation. The technology differentiation, first of all, we are a non-volatile FPGA. Some kind of flash process, Sonos process, means we have the bit stream inside. We don't have to load it at every startup time, but we have it inside. Gives us things like better power footprint, also shorter startup times, so instant on functionality, plus also then topics like security, which can also be interesting for some applications. And differentiation really on that architecture, that's where we put in some limits on where we want to play, also something on the transceivers. We could gear the devices for lower power consumption, and with that really help our clients on using those devices in those space-constrained applications that I already mentioned.
Okay, brilliant. Now, off the back of what you've just been speaking about, can you describe the security aspects of your FPGAs and SoCs? Because I know you said it's quite important. So.
Absolutely. So the security, it always depends on what do you want to treat and what kind of attack vectors do you expect. And the attack vectors are actually very large by now. So it can be the single hacker at home that just wants to prove something.
Yeah.
It can be your competitor, or it might also be a government-graded or a national attack, really depending on where they go. The trouble is, here on the government-graded attacks, it's difficult to do something against. We can still do something.
Yeah.
But also the hacking guy you also already don't want in. But the trouble for them is they can already have equipment for a couple of $100 which can break some of the securities of some FPGAs.
Yeah.
Typical attack vector that you would have is going for the bit stream, or going for, if you have an embedded system with a processor inside, going for the code that is running on the processor. So those really need to be protected. And with the devices that we have, first of all, the non-volatility, we have the bit stream inside. You can't read it back. So that is already one attack vector which is covered.
Yeah.
Also, when we are loading something into the FPGA, the bit stream is always encrypted. So also here with a differential power analysis, it's not possible. We have licensed technology that is protecting us from that. And with that, we can really make sure the bit stream is protected. It's a non-attack vector for us. Then additionally on the processing systems, when you need to run some code, you need to have some authentication running that you know the code that is running on the processor is really your code.
Yeah.
And that's something that we can do before we load it into the FPGA, which also secures us. So Trojan horses, getting some code, malware into the FPGA, we can protect that. The hashing that it would do on that authentication is something one single bit different, and you would immediately have a completely different value on the authentication. You know, no, it's not my code.
Yeah.
And that's just kind of the base level. If you then go one level higher on what the FPGAs and SoCs also have from the architecture perspective, we also have the security devices, which have then a co-processor for crypto co-processing, including a true random number generator. And that's something that a lot of clients are really very interested in, because that means you can do proper encryption based on a real random number, not just kind of pseudo-random.
Yeah.
And that's something really, really important. And then also, from that application perspective, different crypto accelerators for SHA, HMAC, or AES encryption, so that you have also something there. And very often, what you also need to do is, when you do some cryptographic interconnection or communication, you also need to store some cryptographic keys. What we can do is, we have some secure memory on the chip, and that means we can store those keys on the chip. They don't have to be outside, they don't have to be loaded in, which also is always an attack vector. Inside, you can't reach them if you're not the right one, so also protected on that side.
Fantastic, that's a nice range of security features there,
Absolutely.
and an added reassurance for your customers as well.
Absolutely. And from what you see, it's, in principle, it's military-grade security for
Yeah.
the civilian market.
Fantastic. And longevity is sort of one of the key factors in industrial designs as well. So what is your practice around this sort of for your latest generation devices as well as your older ones?
So industrial devices, typically they are running for 10, 15, 20 years or more. And that means you really have to be very, very careful on which components to choose when you do your design.
Yeah.
The FPGAs historically really have moved into the center of the board. So they are the important one. And when you look at our FPGAs, longevity is really an absolute key. We have a non-obsolescence practice. As long as we can sell the devices, as long as we have customers interested in those devices, we are doing our very best to make sure the customers can get that. For the latest generation, currently PolarFire SoC, we are stating as of now 20 years of availability. That means until 2042 at least, and those devices are in the market for already several years.
Fantastic, yeah.
If I look at the previous generation of Smart Fusion 2 Igloo 2, on these we are stating a longevity of at least another 15 years. So 2037 at least.
Yeah.
And those 15 years are something that we have stated already for quite some years. I wouldn't be surprised at all if we are stating that for another couple of years. And Well, talking is easy, but proving is very often more difficult. If you look into our history, the first generations of FPGAs that we had, based from the last millennium, when I was still back in uni, where I didn't have any idea about FPGAs, they are still around. And
Fantastic.
we are still talking today about 10 years of availability for these.
Yeah.
And if you look at, if we would really cancel them in 10 years, which I don't believe, they would have a lifetime of 35 years, so a full working life of an engineer. So take an FPGA of us today and you will retire before the FPGA. That's pretty likely.
Fantastic. Could you describe what sort of process should be expected by anyone who wishes to migrate from a non-microchip FPGA to a microchip one?
The most important bit when you think about migrating from an FPGA to an FPGA is the mindset.
Okay.
People that have already done work on an FPGA, the most important bit is already there. The knowledge of this is an FPGA and I know how an FPGA works.
Yeah.
It's a thinking process which is very different from a microcontroller or processor approach. So that's really the baseline of, yeah, it's good and you'll be able to do that.
Yeah.
The usual next hurdle then is the software. How do I do whatever I did in software A in software B? Our software B would be Libero SoC, that's our IDE. And the good thing about that one is it's a very straightforward software. It's a design flow that an FPGA user knows. It's synthesis, constraints, implementation, and then the debug tools. And those tools are, synthesis tool is Simplify Pro, industry standard tool, simulation, model sim, also industry standard tool, and implementation for us, it's a straightforward tool.
Yeah.
SDC constraints, also an industry standard, so very straightforward to get in. Now, the point also for a lot of people is, okay, I have my design here. How can I get over? How do I create my project? How can I bring in the IP? We have conversion utilities, which are reading in some of some other project files, do an analysis, what source files you have in there, and then those are brought over into Libero SoC.
Yeah.
So typically those are VHDL and Verilog files, and if there is an SDC constraint, we also bring those over and create a project based on the right chosen architecture. That's something that the user would have to bring in. Then you have this project with all the VHDL, and what you will still need to touch is IPs. So IPs either from third parties or also base IPs like a block RAM, a PLL, clock buffering, because those are typically named differently, and that's something that we didn't want to touch. So we give you the users a baseline on where to start, so that they have something to relatively easily start, and then they can do the work. It's a straightforward approach. It's something that an engineer is absolutely capable of. The one thing they will have to do is they will have to go for learning the tool. It's a separate tool. It has a slightly different GUI to what they might be used. Very often still similar enough, but it's something that an engineer can absolutely do. For getting into the tools, we have a lot of videos on YouTube, so also very easy to approach those. Typical approach is go for YouTube, search for Microchip, Libero IDE, and then you will find the usability and how to go for that.
Nice.
And also, if customers really want to get a hands-on, what we are planning on the 4th of July this year in the south of Munich, Hohenkirchen-Siegertsbrunn, is a face-to-face seminar where we are going to do a conversion seminar, full-day seminar, just on the day before the FPGA conference, also located in Munich, where we'll run through such a flow. First of all, showing how the software works, and then doing a hands-on example on a small board, porting a design over into one of our designs. And for people that want to register, easiest way to find that registration link, go to LinkedIn, search for my name, Martin Kellermann, and I did a post on that one. Just have a register there, and you'll find the invitation. 4th of July, Hohenkirchen-Siegertsbrunn in the Arcone Center of Lauterbach.
Fantastic. It sounds like you offer a lot of support to your customers, so that's great to hear.
Absolutely.
And you've previously mentioned that Microchip's process and architecture makes your devices immune to single event upsets. So could you explain sort of what single event upsets are and provide an overview of how your hardware enables technology to avoid such an upset?
So single event upsets are a statistical approach. It's a rare event, but it's an important one that needs to be taken care of. In principle, what it means is you have the silicon die with all the transistors in there, and then you have a charged particle coming in and hitting the die somewhere. It's unknown where, but it will hit somewhere. those charged particles have a certain amount of energy, and that energy on SRAM-based FPGAs has the potential of flipping a bit. A configuration bit is typically the most difficult one or the most important one, and that if it's a configuration bit that flips, it's a different behavior. Maybe an I/O turned on or off, or in a different configuration. It might be a flip-flop that has all of a sudden a different behavior, or a lookup table that also does a different behavior. So it's something that changes the functionality of the FPGA. As I said, it's rare, so a lot of people may think I don't care. It's really, it may happen once every 27,000 years. Well, if you have enough devices, it does, and especially if you have enough devices out in the field, those 27,000 years will very, very easily boil together.
Yeah.
I did some calculations on automotive volumes, 100,000, 200,000 devices out in the field, and then that means it's 3 events per day.
Yeah.
Somewhere in the fleet where you don't know where it is,
Yeah.
and that's something that needs to be mitigated and needs to be taken care of. So for functional safety, it's absolutely essential. And to bring it back to the positive side, Microchip FPGAs don't have that topic. For us, that number is 0. It doesn't happen. And it's not just something that we are saying, but it's proven in measurement by us and by third parties.
Yeah.
So a very simple way of going for functional safety designs, pick the right architecture.
Yes, definitely. Now, Microchip's technology has a strong basis, as you've mentioned, in industrial, medical and automotive designs. So in these areas, what are the power advantages that Microchip's devices have when compared to sort of other competing technologies?
Okay. So I already mentioned this non-volatile technology that we have. And that means we can we can use less transistors for building the functionality of the lookup tables. That means we also have less leakage currents, and the leakage current is something that really exaggerates when you go for higher temperatures. And if you go for a surrounding temperature of 50 degrees, 60 degrees centigrade, then that really kicks in, and that's something where you need to get the heat off the chip. For our devices, that leakage is relatively low. That means we can typically run without a heatsink, where some others that already need a heatsink, or where you already need even worse, a fan. And also looking around here at the show, we have one demo or several demos here with our boards, and all of our boards are completely without heatsinks. You can touch them; it doesn't hurt. You feel it's a bit warm, but it doesn't hurt. On the other FPGAs, it's typically when they're running, there is a fan on it. And just to give some ballpark numbers, if you do a direct comparison, apples to apples, same design, same device size, same design loaded, everything running in the same mode, what we typically see is about 30 to 50% power saving.
Okay.
And I had a very interesting discussion yesterday where I was also quoting that number, and my counterpart was telling me, yeah, it's probably some situation that you made up and which is very much in favor of you. No, it's not. It's a design that I got from a client that gave me an XML file of the information with the power consumption. I put it into our tools and ran the temperature sweep. In this case, it was even beyond the 50% of power saving.
Fantastic.
So for that guy, I could just say, don't believe me, let me prove it.
Yeah, definitely. Well, thank you very much for your insights today. It's been a pleasure speaking with you, and I hope you enjoy the rest of the show.
Yeah, thank you, Paige.
Thank you.